My dear student, colleagues, and all the viewers watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. Today it's our 244 International Physics webinar. I think you have already come to know that the Department of Physics, Pabna, University of Science and Technology, started its online program, including online International Physics webinar. We have successfully completed our 243rd International Physics webinar, including 4 Nobel speakers. So today I would like to welcome you all to a joint session between our department, Department of Physics, Pabna, University of Science and Technology, and the Department of Physics, University of Utrecht, Netherlands. And we have with us here today Dr. Panos Christakoglou, Sir, Assistant Professor, Department of Physics, University of Utrecht, Netherlands, and he has already connected with us. So I'd like to welcome our speaker. Sir, good morning and good afternoon here. Thanks for accepting our invitation, sir. So it's our honor, sir, to host you.
Thank you very much. Thank you very much for this kind invitation.
So dear student and viewers, I think you have already come to know the title of this today's International Physics Webinar. At least very interesting, studying primordial matter in the laboratory. I think you will enjoy it. So sir, you can start your session, and student and viewers can ask questions through comment, and they can also join with us using the link. I will send the link in the comment section, so anybody can join with us.
Okay, super, thanks. So I'll try to go full screen. So I have prepared a few slides, so around 30 slides about how we study this primordial matter in the laboratory. At any given moment, please feel free to interrupt me if you have any questions. So I'll be happy to at least try to answer. Okay, that said, could you please let me know if you see the slides in full screen?
Yes, we can see, sir.
Okay, good. So let me go back then and let me start. Okay, so good morning or good afternoon, everybody. So allow me first to thank again the organizers for their kind invitation. It is really my pleasure to give this seminar, even if it is under these circumstances. So my name is Panos Christakoglou. So I'm a senior scientist at NICEF, which is the High Energy Physics Research Institute in the Netherlands, located in Amsterdam, and a guest physics professor at the University of Utrecht. So my field of expertise is heavy ion collisions, and today I want to share with you a few basic things about this exciting field of research. At least this is how I feel, and I hope that by the end of this talk, you will also see how exciting this field is. So my goal is to give you an idea about what the questions we try to address are, what the tools we use to address these questions are. I'll try to highlight what we know so far, and I will close my talk by briefly mentioning where the field is heading in the near, but also not so near future. So allow me to take you to a virtual tour to Geneva. This was the video that you saw at the very beginning, at the borders of France and Switzerland, where the Conseil Européen pour la Recherche Nucléaire, or better known as from its acronyms CERN, is located. So I mentioned about the question that we would like to address. So the scientific questions we would like to address can be formed in the following way. So what will happen if we collide two large objects that are accelerated at ultra relativistic energies? When I was a kid, these are kind of questions, maybe not at high energies, that a kid would test. We would take toys and smash them together and somehow try to see what the debris look like. And now we are a bit grown-ups, or at least we think we are. And this type of questions is not really an interesting scientific question to answer. On the other hand, one could ask the question, how did the universe evolve after the Big Bang? Can we generate new states of matter at extreme temperatures and densities? So these are two fundamental questions in physics that we try to answer with our research. So the fundamental question we try to address in this field of research is the one being related to how matter behaves at extreme conditions of energy density and temperature. And in fact, this question is part of a list of questions that a rather diverse committee formed by the so-called National Research Council in the United States, who met back in the fall of 1999, defined as the 11 unanswered questions that the high energy physics and astronomy communities were planning to address in the century that we were about to enter. And you see here a list of questions related to dark matter, dark energy. There are also a couple of questions that are also specific to our field of research. The one being related to how the universe began and evolved. So the prevailing picture that we have as far as the evolution of the early universe is concerned is that after the inflation era, so the universe evolved, passing through a series of phase transitions, starting with the electroweak phase transition, followed at lower temperatures by the so-called strong phase transition. And these transitions indicate periods of the early universe with that, let's say, were characterized by extreme conditions. And they are, even at this stage, of a complete mystery. So we have no idea how these transitions look like. So what were the conditions around? The other question that is quite relevant to our field of research is what are the new states of matter at exceedingly high density and temperature? We know very well the theory of protons and neutrons, so how these composite particles are formed by its constituents, the quarks and the gluons. So we know very well this theory, which is the quantum chromodynamics. I'll come back to this a bit later. However, at high densities, these composite particles, the neutrons and the protons, could dissolve into an undifferentiated soup of quarks and gluons, which can be probed in heavy ion accelerators. By the way, these densities, beyond nuclear densities, can occur and can be probed in neutron stars, and still higher energies and temperatures existed in the very early universe. Now, how matter behaves under extreme conditions is not a question that people started thinking about only in the 21st century. So even back in the 1950s, one could see that people like Enrico Fermi, with his studies, stimulated thoughts and ideas that ended up being described in one of his books, the Notes on Thermodynamics and Statistics. Soon after, Hagedorn introduced in one of his studies the idea of fireballs when hadronic matter is compressed. And around 10 years later, first Lee and Wick discussed about what they called abnormal matter, while the possibility of finding such a state in the interior of neutron stars was first discussed by Collins and Perry, followed by what I think is the first discussion about the deconfined state of matter in the paper by Cabibbo and Parisi. However, the state of matter was coined as the quark-gluon plasma, and that will be the focus of my slides. And this is indeed the focus of our research at CERN in a textbook paper by Shuriak. And the initial expectation for such a deconfined matter was that it would consist of weakly interacting quasi-particles forming a gas state. Okay, so all these studies, we fall inside a theoretical framework, which is described by our standard model. So you probably know very well that our standard model attempts to describe the basic forces that we see in nature. We have 4 forces. The standard model describes 3 of them, so it doesn't include gravity, but it does include the electromagnetic, the weak, and the strong interactions. And through some fundamental particles that we still think at this energy scales that we probe that we consider them to be to have no structure. We have the quark families and the lepton families, each of which has 3 generations. So for quarks, UD, charm, strange, top and bottom. I like to call the latter beauty. And so the standard model describes the fundamental interactions and the corresponding particles, and how these forces, how the interactions are mediated by gauge bosons, the photon, the massless photon for the electromagnetic interaction, the 8 massless gluons for the strong interaction, and the quite massive bosons, the Z and the W plus minus, 3 of them for the weak interaction. Okay, and finally, around 2012, the last piece of the puzzle, the missing piece of the puzzle, the Higgs boson, was discovered at CERN. Now, these interactions are described, so you probably know by your courses at the bachelor level, by a Lagrangian density, which for the standard model looks quite scary, quite intimidating, like the formula that you get on the right-hand side part, which was written by Thomas Gutierrez, professor at Cal Poly in the United States. So the fun fact is that Gutierrez, while trying to practically type the whole Lagrangian density of the standard model, he noted a sign error that he made somewhere in the equation. So if someone finds it, please send it to me by email. I'll be more than happy to find it myself. Okay, that said, one of the 3 pillars of the standard model is QCD, quantum chromodynamics. It's the theory that describes the strong interactions. It describes how, the fundamental building blocks of ordinary matter, the quarks and the gluons, they interact with each other. And the birth of QCD is dated back in 1973. It's the latest of the 3 fundamental interactions that fall in the category of the standard model. And its birth coincides, at least in my mind, with a simultaneous publication of these 2 papers by Gross and Wilczek and by Pollinger, who later, back in 2004, got the Nobel Prize for the discovery of one of the basic characteristics of quantum chromodynamics, QCD, which is the asymptotic freedom. Now, also QCD is described by the corresponding Lagrangian density, and if you which is kind of indicated here. So you have the part that describes the quark fields, the part that describes the gluon fields with the field tensor, the part that describes the quark fields, and also their interactions with the gauge bosons, with the gluons. And I mean, if you move forward in your academic career, if you go to the bachelor, to the master's level, and even at the PhD level, you will see such an expression about QCD. And if you compare it with QED, with quantum electron dynamics, the quantum field theory that describes the electromagnetic interactions, you will see that the 2 are very much similar. However, there are hidden differences, which I'll try to highlight here. And the hidden differences mainly come, one of them at least, comes from how this field tensor looks like. For QED, it has only this first component, where alpha is just a vector field that describes the photons. Now over here, this vector field describes the gauge bosons of the theory of QCD, that would be the gluons. However, in QCD, so there is an extra term, and the extra term reveals a very peculiar feature of QCD, which is relying from the mathematical point of view on a non-abelian theory, while QED is described by an abelian group theory, and practically describes or reveals the fact that the gauge bosons of the theory are allowed to self-interact. So there are interactions between gluons, which are reflected in 3 and 4 gluon vertices, which is something that, for example, you cannot see in QED. So you don't see a vertex with 3 photons or 3 or 4 photons. Now, this peculiar nature of QCD is also reflected on how what we call the strong coupling constant looks like. I mean, we keep calling it a coupling constant, but it's hardly a constant. This is reflected on the left-hand side plot, and which shows the coupling strength, so how strong the interaction is, so the strong interaction. If you allow me to use it to describe it like this, as a function of the momentum transfer, that would be how strong, how hard the interaction is, or inversely, this can be translated into scales. So small q values, so small momentum transfers means long scales, so long distances. High momentum transfers means very close distances. So it's inversely proportional, these things, and you see that this coupling strength has a very distinct, a very characteristic, a very strong dependence on the momentum transfer, which tells you that if you probe QCD matter with very high momentum transfer processes or very short distances, then the corresponding coupling strength becomes very small. So this is the region which is called asymptotic freedom, and implies that the interaction, the strong interaction at small distances, is not anymore so strong. It's rather weak. Still, it's stronger than the other two interactions, so than the electromagnetic or the strong interaction. Now, on the other hand, if you go to small momentum transfers or large distances, then what you see is that the coupling strength becomes very large. And in fact, you see that the x-axis over here is cut at 1. So there is also, you have to go to very small values approaching 0, and this curve actually explodes. So which implies that the coupling strength, the strength of the interaction becomes extremely large. So this is the place where the quarks and the gluons are bound together and form our known particles, like the protons, the neutrons, or other hadrons, like the pions, the kaons, and so on and so forth. So this is the place where we discuss about confinement, and how confinement comes about from first principle calculations from the lattice, so from the Lagrangian density of quantum chromodynamics. Is also a bit of a mystery at this stage. Now, this peculiar behavior of the coupling strength of the theory allows us, for processes that involve large momentum transfers, to expand this Lagrangian density in series of alpha s. So in a technique which is called perturbative QCD, which allows you to calculate different processes, and these calculations from the theory side can be compared with experimental data. So they can be confronted with data, and we can make predictions from QCD, which eventually, hopefully, are confirmed by experimental data. On the other hand, for small values of momentum transfer, or large distances again, where the value of alpha s becomes asymptotically large, so this perturbation theory cannot be applied anymore. It breaks down. So one needs to rely on different techniques in order to extract calculations, and this is where lattice QCD comes into play. Now, I'm not a theorist, I'm not an expert, and I barely have time to explain what lattice QCD does very schematically. So what our lattice QCD theorist colleagues do is that they define a lattice, they put quarks at the vertices, at the edges of the lattice, they connect them with gluon fields, they solve the quantum field equations at a given distance between the different quarks, and they do this in steps, and they extrapolate to 0 spacing to recover the QCD continuum. So this is a very computing demanding calculation, which is performed in supercomputers, and the end result is a plot that looks like this, which comes from the so-called hot QCD collaboration, that shows how different thermodynamical properties of the QCD medium behave as a function of temperature. So over here, what you see is the pressure with red, the energy density and the entropy density as a function, so normalized to the proper temperature value as a function of temperature. And what you see here is that around 160, 155 MeV, you see a sudden rise in all these three quantities, which indicate a transition from a deconfined state of matter in this region, the quark-gluon plasma, to our normal nuclear matter, so the hadronic matter, on the left side of the x-axis. So this is practically the phase transition, a strong phase transition that Lattice QCD provides strong theoretical guidance. Now, this transition takes place at extreme densities, extreme values of energy density and temperature. Just to give you an idea about the temperatures that we are talking about, so this transition is expected to take place at around 155 MeV, which if I translate it into normal units that even I will understand, so we are talking about something like 10 to the 12 degrees. I remind you that the temperature in the core of the sun is of the order of 10 to the 7 degrees. So we are talking about a temperature of 100,000 times hotter than the temperature that exists in the core of our sun. Now, this type of conditions, we expect them to be formed in the laboratory and by colliding heavy ions which are accelerated at very high energies. Now, this state of matter has been the focus of intense and versatile experimental programs, systematic experimental programs throughout the last 4 decades or so, starting from Bevelak and AGS in the United States, then the superproton synchrotron at CERN which started in 1987 or so and lasts even until today. So this is an aerial photo, an old one, obviously from the resolution of how CERN looks like, with SPS being this small circle here and the previous accelerator LEP, which is now succeeded by the LHC, being the large circle. So this was the first circle that was used in order to study the state of matter back in the late 80s, early 90s. And what you see here is just an event display of my old experiment, so in A49 at VSPS. And in fact, from these studies of all experiments at VSPS, CERN was able to release a statement practically announcing the discovery of this new we found compelling evidence about the existence of this new state of matter created in collisions between lead ions. However, it is fair to say that the systematic study of this state of matter, of the quark-gluon plasma, has been done in another accelerator complex in the other side of the Atlantic at the Relativistic Heavy Ion Collider, so outside New York in the Long Island, at BNL, where they were and still are colliding mainly gold ions, gold nuclei, starting from 2000 up to even now, even to today. So this is again an aerial view of the RIG complex with, at that moment, the 4 major experiments. Phobos, which is sitting here. Where is Brahms? I don't see Brahms, somewhere here, I think, and then Star and Phoenix, the two latter, Star and Phoenix, being the biggest, the 2 biggest experiments at RIG. Over here, you do see the characteristic event displays from both Star and Phoenix with its characteristic acceptance. And from these studies, people, and mainly from things that I am going to talk about a bit later in my slides, things related to studies related to jet quenching, so mainly how partons, energetic partons, lose energy by traversing through the hot and dense medium, but also anisotropic flow studies, people realize that the system that we create after heavy ion collision is not a gas, a hadron gas, or a gas of quarks and gluons, but actually it's a liquid. So the quark-gluon plasma is a liquid state, and in fact a perfect liquid with minimum, as minimum as it can be, if you allow me to say, resistance between the different layers of the fluid, and this resistance is reflected in one of the transport properties of the system, which is the specific shear viscosity. Now, since 2010, the LHC switched on and started providing lead collisions at extremely high energies, an order of magnitude higher energies than the energies of the previous accelerator complex, RIC. So this, again, an aerial photo of CERN, with the SPS being here now, and this is the LHC. And I mean, there are 4 points. So practically the beams, the proton beams, or even the lead beams, in the case we collide heavy ions, they travel through the tunnel, and they are made to collide at 4 different points along this ring. One of them being at the LHCb. So over here, this is the airport of Geneva, Contren, and this is where CERN is. And just across the street, we have the Atlas experiment. Then we cross the borders, we go to point 2. This is where ALICE, so the experiment I'm working on, is located. And then right across the other part, it's CMS. So CMS and Atlas, so you see 2 event displays here from these 2 experiments, these 2 diagonal displays from heavy ion collisions, that they are mainly focusing on studying the standard model and identifying one of the missing building blocks, the Higgs, which has been discovered, or at least a Higgs-like particle has been discovered in 2012, and through consecutive studies, we get more and more convinced that this is indeed the standard model Higgs. And then LHCb, which is situated here, is mainly focusing on the asymmetry between matter and antimatter, and ALICE is the dedicated heavy ion experiment at the LHC. Now, that said, allow me to make a parenthesis, to open a parenthesis and discuss about a peculiar feature of heavy ion collisions. So normally at the LHC, we collide practically 11 mass per year proton beams. So the proton is really small. But imagine if you put together 208 of these protons and neutrons, that is. So this is how many protons and neutrons the lead ion has. Then the system, the ion, stops being point-like, stops being very small. So it has a defined, let's say, size. And depending on how these 2 nuclei collide, so we have different geometry. We form different geometries. And so this is something distinct with respect to the proton-proton collisions, or with respect to elementary collisions, for example, electron-positron collisions. So, I mean, these are practically elementary particles, or at least we think they are at the scale we probe things. However, nuclei, so our lead ions, are not anymore point-like, so they do have a distinct size. And depending on how they collide, which is something reflected in the impact parameter, so this is the line that connects the centers of the 2 nuclei, so have different geometries. And if the impact parameter is large, then we discuss about peripheral collisions. And this is reflected in the final state by the fact that the number of produced particles are not so many. So in fact, I mean, this is just a snapshot of in the transverse plane of the outcome of such a peripheral collision. And if you have time and patience, then you can even count by eye the number of lines that you see here. So each line corresponds to a particle track that is created from such a collision. So it's they move outwards, and our detectors are able to reconstruct all of these particles. So for such collisions, it might even be feasible to just count by eye for large impact parameters, so the number of particles that are being generated. On the other hand, if you reduce the impact parameter, so if you go from peripheral to mid-central collisions, then immediately the counting exercise becomes a bit tricky. So this is what we call mid-central collision, where more particles are being produced than in the previous case. And if we really reduce the impact parameter to the bare minimum, then we talk about a head-on collision. So this is what is called a central collision, where at the end of the day, you have this mess. And this mess is the mess we have to work with. So I call it a mess, but it's a beautiful mess. It's really a plethora of particles that are being emitted from such a collision, and it's really amazing if you think about this, because our detectors, which are positioned around the interaction point, are able to reconstruct and even identify. By identify, I mean to know what kind of particle each line is. So is it a proton? Is it a pion, a kaon, an electron, even leptons, muon, whatever this particle is. So our detectors are able to reconstruct every single line, practically every single line that you see over here. Okay, and how many particles? Just to give you an idea, how many particles we form. So in a typical proton-proton collision at the LHC energies, we form something like 5, 6, 7 particles per collision. Okay. Now, in heavy ion collisions, in central heavy ion collisions, so we form at the lowest LHC energy, we form something like 1,600 particles in the very central region, so where the Alice detector is situated. So the Alice detector is pretty narrow in terms of what acceptance it covers, what kind of angles, polar angles it covers. Now, if we try to measure all particles in the entire phase space which are being created after heavy ion collision, then you end up having close to 20,000 such particles. So we go from PP collisions from 5 to 7, on average, particles being created, up to 1,600 in the central region, and then you have to extrapolate, and then you get easily to 20,000 particles. So our detectors are capable of actually reconstructing and identifying practically the if not all, the majority, the vast majority of these particles. Okay, good. Now let me close this parenthesis and discuss with you very briefly how we try to study the properties of the quark gluon plasma. And there are two main ways to probe the QGP properties. And over here I have what is called the spectrum, the transverse momentum spectrum of of pions for different centrality classes. So these are very central events, and these are very peripheral events. So the minute you go from up to bottom, then you move from central, very small value of impact parameter head-on collisions to increasingly larger and larger impact parameters, so peripheral collisions, where practically the two ions, they practically graze each other. So there are two basic regions in this plot on the x-axis. The first one being the low transverse momentum region. So you also see from the scale of the y-axis that in the low transverse momentum region, the vast majority of particles are being produced, not only in lead-lead collisions, so also in PP collisions, but in all kinds of collisions. So it's energetically favorable to produce low momentum particles. Okay, and then on top of this, you also have hard processes which produce high momentum particles that I'm going to talk about. So this last part, these are rare probes, and you can, I call them rare, and you can also judge yourself whether my statement is justified or not by just looking at the number of entries that you have on the y-axis. So how many particles are being produced for a given transverse momentum value. So you see over here and you can compare it with this. So these are orders of magnitude differences. So these particles which are being produced with high value of transfer momentum, these are not so abundant. So they are considered to be hard probes. And we discuss about high transfer momentum hadrons, so pions, kaons, protons, and so on and so forth. Then collimated spray of hadrons, which are emitted very close to each other. This is what we call jets. And then heavy flavor particles. So heavy flavor that contain, so hadrons that contain heavy flavor quarks, such as charm or beauty. An example being the charm mesons. So these are the two distinct categories so with respect to the transfer momentum axis, and the corresponding studies can be schematically separated in these two groups. So studies that probe the bulk of particle production and studies that probe the high PT part of the spectrum. So allow me to start with the latter. So what we call QGP imaging through hard probes. So let me try to explain in a nutshell what jet quenching is. I brought it up at the very beginning. Let me try to explain. So we are talking about hard processes with momentum transfers which exceed by far what is called the lambda QCD. So the QCD scale, which is of the order of 200 MeV. So these processes involve momentum transfers by far larger than 200 MeV, so of the order of GeV, more than, so few GeV at least. So this animation, so if I go back, so this animation that I had here indicates how such a hard process emerges from the vacuum. So in the case of proton-proton collisions, then you do have this hard process. You emit a pair of quarks. So they are emitted in the transverse plane in a back-to-back topology just to conserve energy and momentum. So these are fundamental conservation laws in nature. And then these quarks, they cannot fly free. And they simply fragment. They create additional quarks and gluons. These quarks and gluons, they find each other. They form hadrons immediately. And these hadrons, they fly together very close to each other in a spray of hadrons, which we call jets. Okay, so these are processes that involve high momentum transfer. And as I said at the very beginning, so these are processes that can be calculated through perturbative techniques from the theory, and can be confronted, these calculations can be confronted with what we measure experimentally. And what do we measure experimentally can be seen on the right-hand side plot, which shows you the energy deposited in calorimeters, some detectors which where our particles hit the sensitive areas. We pick up the signal and we reconstruct. We are able to count not only how many particles, but also the energy with which these particles hit the detector. And it turns out that in such case, in the case of proton-proton collision, where you do not form a quark-gluon plasma, then the two energies, they are very well balanced, as you see. So they are of the order of 250 GeV. Please keep in mind that this comes with the corresponding uncertainty, and also which implies that these are two very well balanced jets. Now, this thing changes drastically, radically, when we move from proton-proton collisions, where we do not expect to form a quark-gluon plasma, to collisions between heavy ions. Over there, you form a quark-gluon plasma. The partons that are being emitted through this hard process, they interact with the medium. They can lose energy via either collisional or radiative energy loss. So they radiate, for example, gluons, as I indicate over here in this cartoon sketch. So there can be that one of the partons doesn't have so much medium to traverse, so it will radiate gluons, but not so much, because the length that it travels is not that much, and it will exit the quark-gluon plasma region. Allow me to say it roughly like this. It will start fragment, create hadrons, and these hadrons, they will form again a spray of hadrons, which we call jet. On the other hand, in the back-to-back topology, energy and momentum conservation, it can be that the other parton, which is formed from this high momentum transfer process, has to traverse a by far larger area of quark-gluon plasma, and thus it will emit more gluons, it will radiate more, it will lose energy. I mean, the energy is not lost, it's distributed to other soft partons, and it will fragment at the end also and create a second jet, but this second jet will be not as energetic as the first one. It will be of lower energy, and it will also be broader, okay, because of the fact that this parton has been interacting with the medium by far more than its partner. So the experimental consequence will be a suppression of high transverse momentum particles and attenuation of the energy of the jets and the modification of soft particle production. So just to give you an idea, because obviously I cannot describe this in so much detail at this stage due to time. Just to give you an idea how this the previous picture of this calorimeter measurement looks like in the case of heavy ion collisions. Then you have these two peaks, which reflect the energy deposited in calorimeters by these two jets. So you have this jet, which is probably produced in the surface, which is reflected in this large tower with large value of transverse momentum, large energies. On the other hand, the back-to-back jet, so its partner, is not so energetic as this one. So it's not that energy and momentum is not conserved. That's not the case. It is just that this second jet has been interacting with the medium more because it has traversed larger path inside the medium and lost energy. In fact, didn't lose it. Well, it lost energy, but the energy is not lost. It's distributed to softer particles. Good. Now, let me jump briefly to the low PT part, so the bulk of particle production. Over there, the main study, one of the main studies, one of the main phenomena that allows us to say something about the nature of the quark-gluon plasma is what we call an isotropic flow studies. And I will try briefly to sketch how this thing comes about, what is an isotropic flow. So what you have here is this cartoon sketch with the two ions. They fly in opposite directions. In the case of a peripheral collision, in the case of a collision with large impact parameter, so the line that connects the centers of the two nuclei, then not all the entire surface of the ion collides, but only part of it. So this red part, the remaining part of the ions that do not collide, they do not reside in this overlap region, they just fly away. This goes in this direction, and this goes in that direction. And I hope that you can see my cursor. Now, if we see how this collision looks like in the transverse plane, then you have one ion coming, let's say, from the screen outwards, and then the other ion that comes from outwards towards the screen. I indicated them with different colors, so they do form an overlap region, and this overlap region looks to first order, very idealistically thinking about this, like an almond shape. And what is also important is what we call the reaction plane, which is the plane which is defined by the impact parameter, again, the line that connects the centers of the two nuclei, and the z-axis, the line on which the ions traverse. So this is another representation. So if you want to picture it a bit better, of how this reaction plane looks like. So this gray area. So what you form at the very beginning is an anisotropic system. So it's not a round shape, right, which is pretty isotropic, but it's an ellipse which is characterized by its special eccentricity in coordinate space. So you can have two extreme conditions. So you can either have, I mean, this overlap region contains different, so nucleons, so protons and neutrons from the different nuclei, from the two ions that collide. And we can think of a heavy ion collision as a superposition of independent nucleon-nucleon collisions, protons on protons, protons on neutrons, neutrons on neutrons from the two different ions. Okay, so if this is the case, then the final state particles which are being emitted from these independent collisions will have their momenta pointing at random directions. So at the end of the day, the azimuthal distribution that you will see as a function of, so the azimuthal distribution that you will see for the emitted particles will be pretty flat. So there will be no preferred direction. On the other hand, we can have the development, the other extreme case would be the development of a system which is driven by its high density and pressure at the center of the fireball. So you have larger pressure, which is here along this axis, which is the short axis, what we call in plane, and slightly smaller pressure along this axis, what we call out of plane, so the long axis of the ellipse. So we form asymmetric pressure gradients, so larger pressure in plane than out of plane, that actually push matter outwards, but it pushes matter outwards also in an anisotropic way. So this is how anisotropic flow develops. And at the end of the day, the particles which are being emitted from such process will have a distinctly different feature than the one that we saw before, where the momenta were pointing at random directions. So over here, because there is a preferred direction, and that will be in plane, so you get larger push in this direction than in that direction. So the experimental consequence would be that you will have more and faster particles traveling in the short axis than in the long axis. And that would be reflected in an azimuthal particle distribution that will not be any more flat, but it will have this cosine modulation, which we can measure and we can fit it and we can describe it with a series, a Fourier series, the coefficients of which are what we call the flow harmonics, with V2, elliptic flow, being the dominant one, which reflects the highly anisotropic initial state with which we start a heavy ion collision. Okay, so I mean, very briefly, anisotropic flow is nothing else than a translation of coordinate space anisotropy into momentum space anisotropy. Okay, so this is what I try to described before with these cartoon sketches, and the study of this anisotropic flow phenomena has been instrumental in realizing that the quark gluon plasma that we create after a heavy ion collision at RIC, but also at the LHC, is not a collection of, so it's not a hadron, a parton gas, a gas of quarks and gluons, but in fact, it's a liquid. And in fact, it's a perfect liquid, and perfect in a sense that the resistance of different fluid elements to different velocities is minimum. Okay, so we know very well, for example, different liquids. We are very much familiar with how, for example, honey behaves or how milk behaves. So I mean, so if you apply a velocity difference in different layers of honey, let's say a jar of honey. So you try to devise an experiment where you give some velocity to the lower part and a different velocity to the upper part. So and you measure these velocities of the different layers with time. Let's imagine that you could do this. Then you will see that very quickly these velocities will be equalized. So honey is a liquid, if you can call it like this, with very large shear viscosity, for example, specific shear viscosity. The QGP is a liquid with very low value of shear viscosity, practically very close to the lower limit, very close to zero, if you wish. Okay, and this is what I try to illustrate here. So you have an initial state where you do have velocity differences between different layers of a fluid. And in the case of zero value of specific shear viscosity, then these velocity differences will be carried through the entire process and will be reflected in the final state. If, on the other hand, you increase the specific shear viscosity, and let's imagine in the extreme case this goes to infinite, then these initial velocity differences between the different layers of your fluid will be equalized very quickly. Okay, so this is what specific shear viscosity does. Now, I mean, also with the minute the LHC was switched on, so we were able also to confirm that also the LHC, the coagulum plasma, behaves as a liquid, or also as a perfect liquid. Where what we are moving forward is to characterize in a bit more detail the coagulum plasma, and by performing different studies, one is able to probe for the first time the temperature dependence of the specific shear viscosity and the connection with the equation state. So the equation that shows how different thermodynamical properties of variables, parameters of the coagulum plasma, so temperature, pressure, energy density, how they are connected. So this is what we try to do at the LHC by performing precision measurements. Okay. Now I have a cartoon sketch here indicating, I mean, summarizing what we know so far as the time evolution of heavy ion collision is concerned. I mean, and this is something that we derived from all the studies that we did, jet quenching studies and isotropic flow studies. So we start off with two nuclei because they are accelerated close to the speed of light. They are largely contracted. Depending on the value of the impact parameter, again, I stress this is the line that connects the centers of the two nuclei. They form different geometries that are also affecting the final state. Now, the overlap region resembles to first order an almond shape, which provides the dominating ellipticity in the initial state in coordinate space, which is translated into the final state elliptic flow in momentum space. Now, the initial state, so after, let's say, less than 1 Fermi over C, the initial state is characterized by the lumpiness of the density profile. This is a result of quantum fluctuations in the positions of nucleons inside the nuclei, which are different from event to event, from one collision to the other. At the same time, both soft and hard QCD processes, latter with large momentum transfers, take place and provide the means for rapid thermalization of the medium of the coagulum plasma, which is formed after 1 Fermi over C. After this stage, a strongly coupled liquid, the coagulum plasma, is formed with a very small mean free path. The medium expands explosively outwards, as I discussed before, an expansion driven by the non-uniform energy distribution in the initial state in coordinate space, which actually creates these pressure gradients I was talking about in the QGP stage. Now, the evolution of the coagulum plasma is described by hydrodynamical models that usually employ viscous corrections as reflected by transport coefficients such as the shear and bulk viscosity over entropy density ratios, things that I discussed just before. After this stage, the parts of the QGP that cool below the deconfinement temperature will hadronize, will produce hadrons, pions, kaons, protons. And thus, we have the formation of a gas of hadrons, this time mainly pions, which are the lightest of the hadron family. But also you will have kaons, you will have protons, which are formed. And these hadronic states, they will interact with each other, they will collide, they will interact elastically, but also inelastically. And these processes are usually described by models, which we call hadronic afterburners, such as QMD. Now, in addition to these hadronic probes, we have hard processes that usually occur at the initial stage, such as the creation of charm quarks, like this guy here, and in general, heavy flavor quarks, energetic quarks, and gluons that fragment, create spray of hadrons, which we call jets. These jets interact with the medium, either via collision or radiative energy loss, and you have the effect of jet quenching. And from these studies, we are able to say a lot of things about the nature of the QGP. At the end of the day, and after, let's say, around 10 Fermi over C, which is really very, very, very small fraction of a second, so something like 10 to the minus 23 seconds or so, 10 to the 24, 10 to the minus 24, sorry, then you form, so that all these particles that they fly away, they're picked up by our detector, which are able to reconstruct them. Okay, that said, allow me to just go through very quickly to what we have been seeing also, not only in collisions between heavy ions, but also in collisions between small systems. So the heavy ion program has been expanding also by looking at collisions between small systems, not only heavy ions, but also protons on ions, but also protons between each other. And these were systems that we used to consider as reference systems. We were not expecting them to form a hot and dense QGP, a hot and dense QCD medium. However, so there is a change of paradigm that took place starting from 2010 at the LHC, and where we started seeing similar effects. I don't have time to go into detail. So these are nice, colorful plots that indicate the phenomenon of this anisotropic flow, which is formed also in heavy ion collisions. This time we have its reflection in collisions between two protons at the LHC in 2010, reported by CMS. But also similar features as the ones that we've seen in heavy ion collisions. And again, this is the elliptic flow, and this is how elliptic flow develops as a function of PT for different particle species. And you see that for a given value of PT, the larger the mass of the particles, so these are protons, the lower the value of V2 is. And this is a characteristic feature of how the system expands anisotropically outwards. So this is a characteristic feature of the formation of the QGP and its expansion. So we see similar features now, not only in lead-lead collisions, in heavy ion collisions in general, but also in collisions between small systems, which probably justifies the expression that a compatriot of mine used to say, Heraclitus, back in ancient times, that tapadari, which means everything flows. Now, there has been a lot of progress that we made in all these years, and this progress is also reflected in how well we have been able to constrain the basic properties of the quark-gluon plasma, one of which is the specific shear viscosity that I discussed before. And you see how well by the judging by the size of the band, how well we can constrain this property, this parameter, as a function of time. But there are a lot of things that we need to do more, and I list some of them. By performing additional measurements for heavy quarks and jets, we can improve our knowledge of poorly constrained parameters. We can constrain new phenomena very closely connected to parity violation in strong interactions, for example. We can try to find the origin of these collective effects of the anisotropic flow effects that we see in small systems. So do we form a quark-gluon plasma also in collisions between two protons, for example? And there are also other things, one of which is quite interesting, the connection with gravitational wave physics. At the very beginning, I kind of hinted that there is a very strong connection with the nature of the interior of neutron stars. For example, over there, we might have, for example, in neutron star mergers that produce gravitational wave signals, we might have the formation of a deconfined state of matter, which the signatures of which can be reflected in the gravitational wave signal. So which makes the connection between the two studies, the two fields of research, quite interesting to pursue. At the end of the day, what we do need to do is to discover the propic microscopic picture that describes the macroscopic behavior of the quark-gluon plasma. Now, the last couple of slides, very quickly. So the future is quite bright in this line of research. So there are quite a lot of plans for the next years. So for the medium term plan, so we have low energies at NICA, in Dubna in Russia, and at CBM at FAIR in Germany, so that are going to study the baryon-rich environment, so at very low values of energies, square root of S, center of mass energy per nucleon pair. At intermediate energies, the successor of Riga experiments will be Phoenix, will start collecting data in 2023. And then the LHC experiments, we are currently in a shutdown mode. We are finalizing our upgrades in the next period of 8 years, up to 29 or so. We will be having what is called run 3 and run 4 at the LHC, collecting data at large energies and analyzing them and trying to figure out more and more about what the quark-gluon plasma looks like. Now, at the end of the day, even beyond 2030, so that there is a very first attempt to solve some thoughts about extending these studies at the LHC by first of all designing a new modern detector, very fast detector, which is going to focus on multi-heavy flavor states, quarkonia states, exotic states, and also one of the characteristic signatures of the strong phase transition, and that would be chiral symmetry restoration, which is quite elusive and so far has not been studied systematically in detail for very good reasons, of course. Now, that said, I would like to thank you for your attention. I got carried away, I think, with time. I am already talking for 1 hour. Apologies for this. So I was not interrupted. If you have, however, any questions, feel free to ask.
Yeah, thank you, sir, for your wonderful and excellent lecture. So we have got few questions. So if you allow, we can start our discussion session, sir.
Sure.
Okay, sir. I can add the question in the screen. I think you can see the screen.
If I can
go the SteamYard page.
Yeah.
Okay. The first question. Can we detect and study the neutrinos produced just after the Big Bang and get some knowledge about the primordial universe?
Okay, so that's indeed a general question. Now, I mean, so there are attempts to study. I mean, okay, so let me start by saying that neutrinos are quite elusive particles to detect. Okay, and the reason being that they hardly interact with matter. Okay, and I mean there are specific experimental programs that look at neutrinos, and they do try to find. I mean, for example, the mass hierarchy and so on and so forth. I mean, then also to do detailed studies about this category of particles. However, as far as heavy ion detectors are concerned, that they are really not suitable for studying neutrinos. Okay. Now, if you want to, so then you have to go to a different experiment and somehow try to study this. But in principle, I mean, yes, one can perform such studies, but I mean, neutrinos, as I said before, they are quite difficult particles to detect. I mean, I'll just throw a couple of names of experiments so that you can somehow try to find more information in your free time. So think about IceCube, think about Antares, KM3Net, think about a future experiment with neutrinos that will be June, that will be located in the United States. So of course, so Kamionokade, so Super K in Japan, which is one of the pioneering complexes which study that focus on neutrino physics. So try to Google this and from there try to go there and to the corresponding experiments and try to find extra information about this. I do think that it's a quite exciting field of research. It's not just not my research at this stage.
Sir, thank you. There is another question. So can string theory tell something about the primordial matter?
Yeah, in fact, I mean, this is a nice very, very nice that you mentioned this, because I mean, surprisingly, we realized that through string theory, or at least the flavor of string theory models, so that actually we're trying to study phenomena related to gravity, to black holes and gravity. One is able to find a dictionary and make the connection between gravity studies and what we study in heavy ions. So I mean, one thing that you can try to do, for example, is try to read about the so-called ADS-CFT correspondence, which makes this translation from the gravity duality to the ADS-CFT duality, and has something to say about the quark-gluon plasma.
Okay, sir. Thank you. We have another question. So, how can it be known if a black hole is primordial?
Yeah. So I mean, okay. So that there are, again, I'm not an expert on this, so that there are, however, distinct signatures in, for example, gravitational wave signals. And in fact, I mean, currently LIGO and Virgo, they do have some studies, or at least they plan to have some studies for detecting primordial black holes. There are characteristic signatures of the gravitational wave signal coming from primordial black holes and let's say black holes which are formed later. But obviously this is so far the answer is negative. I mean, the sensitivity of gravitational wave signal detectors at this stage is also quite limited. But I mean, starting from 2030, so there will be two new detectors which will be installed. The first one will be the Einstein telescope. That will be a ground-based detector, but also a space detector, LISA. So I mean, both of them they cover different ranges of the frequency spectrum. The combination of the two will be probably, or at least people think or hope, they will be able to detect, let's say, gravitational waves coming from primordial black holes.
Yes, sir. Thank you. We have another question. So, does primordial black holes have connection to dark matter, and how are they connected? And is dark matter in our universe formed by primordial black holes?
Yeah, I mean, if I try to answer this question, I would be speculating, right? I mean, we call it dark matter for a very good reason. I mean, whenever you hear physicists calling something dark, so it means that we have no idea what this thing is. I mean, we thought dark matter is a characteristic example. I mean, dark energy is another example. I mean, lately also dark energy is also doubted that it exists. So it's also something like this. I mean, we don't know what dark matter is. I mean, we have some idea where we could look at, but I mean, we see experimental observations that can be explained through the existence of dark matter, but at this stage we have no idea what this dark matter is and how is it formed and what it consists of. So I wouldn't know. I mean, yeah, if I would say yes or no in this. So I mean, there are also theories that connect these things together. But I mean, you need experimental evidence to make a solid case.
Okay, sir. Okay, sir. Thank you. We have another question. So, are there ways to know how old a black hole is? Is there primordial black hole in the observable universe? And what are the lifespan of the black holes? And how can we know?
Yeah, again, I'm not an expert on black holes and on physics of black holes, but I mean, so there are ways to find out the age of stars in general, and looking, for example, at the mass of a black hole, and then looking at many things around the black hole. One could probably say a few things about the age. And as far as the primordial black holes, maybe there are. I mean, we have to see. I mean, so you do have, at any given moment, I mean, the message that I would like to convey is that, I mean, there are plenty of theories, okay? But every single theory needs to be confronted with experimental data. So first of all, every single theory needs to propose something that can be tested experimentally, okay? Otherwise, allow me to say it maybe provocatively, it's just a beautiful theory. So it needs to provide the prediction that can be tested. And then based on this test, on the experimental test, then we can either discard the theory or approve the theory and make it our prevailing theory.
Okay,
so
sir.
In that sense, primordial black holes we haven't seen so far.
Thank you, sir. We have another question. So what is the primordial universe theory, and what is primordial soup theory? So is it true? If not, in the future about these topics, using future technology, what should they create and study and look into the successfully create about these two topics and prove it? The big question.
Yeah, I mean, yeah. So I mean, the whole idea about, so the prevailing theory that we have is, I mean, about the evolution of the universe relies on the so-called Big Bang, the inflation era, the phase transitions, electroweak and strong phase transitions, I mean, nucleosynthesis, and the formation of stars and galaxies. So this is, roughly speaking, what the prevailing, and very, very roughly, and very quickly. So I don't even give justice to the theory, obviously. So how this theory looks like. I haven't heard about this primordial. What do you mean by this primordial soup theory? So maybe you want to say that the QGP existed at the very beginning, which I think it's a plausible thing to say. And I mean, if you go back in time and somehow try to reproduce the conditions of the universe as a function of time, then you will reach a point where indeed you expect a quark-gluon plasma to be formed at the very beginning. Now, what is the effect of the nature of the quark-gluon plasma to the evolution of the universe? So this is something, this could be a very good question that the cosmologists need to answer. And that, I mean, it's a long shot of what I'm going to say. So this is also something that could make the connection between cosmology and what we do in heavy ion physics. But of course, this is something that needs to be, so maybe what we measure is not, so for example, the shear viscosity over entropy density is not really relevant for them. Certainly it's not really relevant for them at this stage with the level of accuracy that these cosmological studies have, in my view. But maybe later on, so the minute they have more precise measurements, maybe they will realize that, so the nature of the QGP at the early universe might be quite relevant.
Sir, thank you. There is another question. So it is said primordial galaxy is a galaxy that formed very early in the history of the universe. Is there primordial galaxies in the observable universe? With this info, what is the lifespan of the galaxy?
Yeah, so also there I would not be able to answer very, very precisely. So I mean, it's I described it before. What is the prevailing picture of the evolution of the universe? And at some point you start forming stars. At some point, dust becomes a bit more so star dust elements that they just attract each other. That you have higher density regions in the sky. So you just form, let's say, lumps. Lumps become larger and larger, and this is how we think stars have been were formed. And then you start forming galaxies by gravitating different stars together, and somehow try to rotate around the center of the galaxy, and so on and so forth. But this happens further, so a bit later. Now, I mean, these primordial galaxies is also something which is a bit, again, one needs to discuss with cosmologists and try to see whether such thing exists.
Yeah, this may be the last question. So what is the primordial quantum fluctuation, and how does it explain how the universe went from nothing into something? And what can we study into it more in the future to discover more factors about the birth of our universe?
Yeah, so also here, I mean, so these quantum fluctuations, I mean, the only thing that I can say is the one which is very much connected to what we do. I mean, it's not the same thing, obviously, because we discussed about different scales. So when you collide two ions and when the universe was formed, because, I mean, in principle, so these quantum fluctuations, what they do is that they provide the means to provide the means to form some asymmetries in the distribution of matter in our collisions, but also in the early universe. So at the end of the day, you see that it's not everything is not really isotropic, for example, and this is practically a result of, in our case, of these quantum fluctuations, so the initial state quantum fluctuations. Now, again, keep in mind that I'm talking about heavy ion collisions, and the translation or the extrapolation down to how the early universe looked like involves quite some assumptions, and obviously there are significant differences in scales and in conditions and so on and so forth. I mean, cosmologists will tell you even more. But this is more so. I mean, turns out that also in our case, but also in the case of the early universe, these quantum fluctuations, they do play quite a significant role in forming these anisotropies that we see in the final state.
Okay, sir. Thank you for your wonderful presentation and nice discussion session. It was a great opportunity for our students and viewers to learn a lot of things about the primordial matter. So thanks again for giving us this opportunity, sir. And hopefully in near future we can arrange another webinar. And after the COVID, when everything is fine, I'll definitely invite you to our university for a face-to-face session, and that will be great for our student also. So thanks again, sir.
Very good. Thank you very much for the invitation again, and thanks for your attention. Thanks for these very nice questions, and I hope to see you guys soon.
Yes.
Thank you very much.
Have a nice day.
Bye.